Welcome to 4.1, vector spaces. So this is going to be an exciting chapter. I found this on the internet. I kind of like this little note from the teacher. Indeed, +1. So intro and motivators. Giuseppe Peano was the first person to explicitly lay out what a vector space was. People had a notion before then of what a vector space was, but he made it formal. Vector spaces occur all the time in nature. In fact, here are two examples. Solutions to homogeneous differential equations form a vector space. So if you're in differential equations, those two examples will be of interest to you. The vector space axioms, there are 10 of them, and you don't have to memorize them. A vector space is a set of objects, and we call those objects vectors. And the operations on a vector space are addition and scalar multiplication. And the vectors have to obey these 10 axioms. Now, the real numbers obey these 10 axioms. So these are fairly familiar axioms, like addition is commutative, addition is associative, so on and so forth. So I'm not going to go through and read those with you. What I'm going to do is jump in and do some examples with you. Here are some vector space examples. Rn, which is the set of column vectors with n entries, is a vector space. So for example, here's a picture of part of R3. Let me make this pen a little bit thicker. So I've listed 3 vectors in R3, the 0 vector is in there, and then here are 2 other vectors. Those form a vector space. All vectors with 3 entries, not just those 3 vectors. Matrices form a vector space. M by n matrices. Here's an example of M22, 2 by 2 matrices. They form a vector space. You can add them together. You end up with another matrix, 2 by 2. The 0 vectors in there. For every matrix, there's a negative, every matrix M, there's a negative M with such that when you add them together, you get the 0 vector. Continuous functions form a vector space. You can add continuous functions. You can multiply continuous functions by a scalar, and you still have a continuous function. And finally, the big examples we're going to be working with are Rn, M22, and Pn, which is polynomials of degree less than or equal to n. Those form a vector space. Here's a picture of P2. The 2 goes at the bottom, whereas with Rn, the n goes at the top. So this is the set of polynomials of degree less than or equal to 2. Those would be quadratic polynomials. Let me show you here. If I take Q and R and add them together, I actually get 4t, because the negative t squared adds to the t squared to be 0. I get I get positive 4t. That's a polynomial. This has degree less than 2. It's got degree 1. And so that's why it's important that when you remember the definition of this, you remember that these are polynomials of degree less than or equal to n. So that when you, because here I added a polynomial of degree 2 to another one of degree 2, and I got one of degree 1. But that's okay, because I'm still living in P2. That's a polynomial of degree less than or equal to 2. So let's talk about subspaces. A subspace of a vector space is a subset. So here's a vector space V. H is a subset, and it's actually a mini vector space living inside of V. So it's not just any subset, it's a subset that follows these 3 axioms. The 0 vector lives in H. So we know the 0 vector lives in V because V is a vector space, so it has to have the 0 vector. But actually, the 0 vector lives in H. So 0 lives here. It's in both V and H. H is closed under addition, which means if I take 2 vectors U and V in H, U and V in H, I know when I add them together, I stay inside V because V is a vector space, all right? So U plus V could be out here, but it's not because I'm insured by axiom B. If u and v are in H, then u plus v stays in H. So u plus v lives inside of H. Same thing with any scalar times a vector in H, you stay inside of H. So it's a little mini vector space living inside of V. And those axioms, A, B, and C, are what ensure that you actually have a vector space, because all the vectors in H live inside of V, so they follow most of the axioms of V. The only ones you have to ensure are 1, 4, 6, and 5, and that is done by the subspace axioms. Okay, proper subspace. Every vector space has two subspaces, the zero vector space and the whole vector space itself. To distinguish between those two extremes and a typical subspace, we define a proper subspace, and that's any subspace that's not one of those two extremes. And it's possible that a vector space won't have any subspaces aside from those two extremes. But let me show you some example of things that are subspaces and things that are not, and how to show. So for example, if you look inside of M22, which is the set of all 2 by 2 matrices, and you look at all the diagonal matrices, so those are 2 by 2 matrices that look like this. There's 0 entries on the non-main diagonal, and the main diagonal, the A and the B, they could be 0, but they don't have to be. So those are called diagonal matrices that have that form, and I claim that that's a subspace. So there are 3 conditions to show according to the subspace definition. And by the way, you do need to know this definition. You don't have to memorize the vector space axioms, but these you do have to know. So number 1, is the 0 vector in D? Well, yes, the 0 vector looks like this. That's certainly a diagonal matrix, because 0 and 0 are real numbers. So that works. Now I take 2 diagonal matrices, U, and this is a typo, that should be V, U and V, they're diagonal. I have to show their sum is in D, so that would be axiom B. U plus V is A0, 0B plus C0, 0D. Okay, and that's A plus C, 0, 0, B plus D. Well, that's another diagonal matrix, so that's in D. So some of these, just showing these properties are true, it's just a formality, but it does need to be shown. So that one works, and then the only other thing to show, according to the definition of a subspace, is that scalar multiples, let's see, a scalar alpha. Okay, so alpha U, we have to show that scalar multiples stay inside of D. So that's alpha times the diagonal matrix A0, 0B. That's alpha A, 0, 0, alpha B. That's still a diagonal matrix. So H is indeed a subspace of M22. Sorry, I'm saying H, but I meant D. Okay, R2 is not a subspace of R3. This always comes as a shock to some students. R2 is not a subspace of R3. Here's why. R2 is not even a subset of R3. So let's go back and look at the definition of subspace. It's a subset of a vector space V. So the elements in H, first and foremost, have to live inside of V. They have to be a subset before they could possibly be a subspace. A subset is just a collection of vectors, okay? So you could have a collection of vectors, but those vectors don't satisfy these 3 requirements. In this case, it's worse than that. We don't even have a subset. So vectors in R2 are not in R3. So here's an example. For example, e.g., 1, 2, that's a vector in R2. That's not in R3. So R2 couldn't possibly be a subspace of R3 if it's not even a subset. However, there is a copy of R2 that lives in R3, and that might be what you're thinking about when you think, well, R2 should be a subspace of R3. For example, here's a picture of R3. The XY plane is like a copy of R2 that lives inside of R3. So how do we get that to work? Look at the vectors of the form A, B, 0, where A and B are any real numbers. That's a copy of R2, right? A and B can be anything, but the Z coordinate is 0. That does form a subspace of R3, and it's a subset of R3 because there are 3 entries in those vectors. So let's go through and show the 3 conditions hold. The 0 vector, that's certainly in H, because 0 and 0 are real numbers. Let's show closed under addition. If I take 2 vectors in H, so 2 vectors that have 0 Z entry, and I add them together, I get A plus C, B plus D, 0. Okay, that third entry is still 0, so I'm still in H. Good. Now, the last thing, show that a scalar multiple times a vector in H is still in H. So Cu is equal to Ca, Cb, 0. I still have 0 third entry, so I'm still in H. Okay, so H is a subspace of R3. All right, let's look at another example, and I'm going to show this H is not a subspace of, in this case, R2. So let H be the union of quadrants 2 and 4 in the plane. So these are vectors in R2. And I'm going to show H is a subset of R2. Here's R2. H is vectors over here and over here, because when you multiply the 2 entries together, you get a number less than or equal to 0. That means either X is negative or Y is negative, but not both. That's a subset of R2. It's not a subspace. So, is the 0 vector in H? Actually, it is. So not all the parts of the definition have to fail. Only one of them has to fail in order to have not a subspace. So the 0 vector is in H because 0 times 0 is less than or equal to 0. That holds. So 0, 0 is in H. All right. Scalar multiples are also in H. So if I take a vector in H, so it's in quadrants 2 or 4, and I multiply by a scalar, I claim that that scalar times U is still in H. So here we go. Cu is CaCb. Okay, let's look at the product of Ca and Cb. We're trying to show it's less than or equal to 0. CaCb is C squared times AB. That's less than or equal to 0 because AB is less than or equal to 0. Why is AB less than or equal to 0? Because U is in H by supposition. So if U is in H, that means automatically A times B is less than or equal to 0. C squared is positive. Well, it's non-negative. It could be 0, but it's certainly not negative. So this condition holds. So Cu is contained in H. Where H fails to be a subspace is that it's not closed under addition. So here's an example where I'm going to find 2 vectors. They're both in H, but their sum is not in H. So there are infinitely many examples you can use. The ones I came up with U equal, let's try X is -1, Y is 2. So that's in H because it's in quadrant 2. And then V take x is positive 2, y is negative 1. That's in H because it's in quadrant 4. U plus V, if I add them together, I'm going to bop out of quadrants 2 and 4. So if I add them together, I get negative 1 plus 2 is 1. 2 plus negative 1 is 1. Uh-oh, that's not in H anymore because this is in quadrant 1. So H is not closed under addition. So there's an example where you have a subset that is not a subspace. Sometimes it's helpful when you're trying to understand a definition to see examples of that thing and examples of not that thing, if that makes any sense. Okay, so this is exhausting. To show H is a subspace seems like a very long process for every, you have to take generic vectors and show that their sum is in H and their scalar multiples are in H. There's a quicker way. It doesn't always work, but for the most part, if you can show that a space H is the span of a set of vectors, then it's automatically a subspace. Okay, so the theorem is, if you take vectors from a vector space, their span will form a subspace. So if you can show that your space is the span of a set of vectors, then you've automatically shown it's a subspace. Couple of examples, subspaces of R3. Well, we know the zero vector is a subspace of R3, and all of R3 is a subspace of R3. But are there any proper subspaces of R3? Yes, there are two types. One, if you take a non-zero vector and you look at its span, that forms a line through the origin and the vector v, v1 in this case. So lines going through the origin, those are subspaces. Any line through the origin in R3 forms a subspace. Any plane through the origin forms a subspace. Planes are the span of two vectors, and those two vectors have to be linearly independent. So if you take two vectors, one is not a multiple of the other, and you take their span, you're going to get a plane through the origin. So that's a nice way to visualize subspaces. All right, here's an example of using the theorem. Let H be the set of all vectors of this form, where A and B are real. I didn't write that, but it's implied. Show H is a subspace of R2 by finding two vectors such that H is the span of those vectors. So let's look at this vector more carefully. A, 2A plus 2B minus 3B. This is a single vector. Let's write it as the sum of two vectors, the A part and the B part. A, 2A plus 2B negative 3B. Okay, now let's pull out the A. Remember, A is any real number. A times 1, 2. And let's pull out the B. This is 2, negative 3. Well, vectors that look like that are simply in the span of 1, 2, and 2, negative 3. So H is equal to the span of the two vectors 1, 2, and 2, negative 3. If you take all linear combinations of those two vectors, that's exactly the set of vectors A times 1, 2 plus B times 2, negative 3. That's how H is defined. So that is a subspace of R2. Not just a subset, it's a subspace. Okay, and here's another one. H is the set of these vectors. These vectors live in P2. We want to show H is a subset of P2, not just, a subspace, not just a subset. So list four vectors in H. So, well, I could take A to be 0, the 0 vectors in H, and then I could take A to be 1, t squared. I could take A to be negative 1, negative t squared. I could take A to be 2, 2t squared. All multiples of t squared are going to be in H. So I could show H is a subspace by verifying the axioms in the definition. I could go through the long, arduous process. It's not really long or arduous, but I could go through and show that these three conditions hold by hand, or a quicker way, I could just show H is the span of a set of vectors. So how about this? H equals the span of the single vector t squared. In P2, vectors are polynomials. So I'm calling it a vector, but it's a polynomial. So vectors are polynomials. H is the span of that single polynomial. This is, by definition, the span of t squared is the set of all multiples of t squared. So H is a subspace. All right, so little recap here before I set you loose to do some practice problems at home. So we're getting into probably different territory for you, talking about vector spaces and how could a polynomial be a vector or a matrix be a vector. So it's going to expand your mind a little bit. Subspace recap. The quickest way to show a subset is a subspace is to show that that subset H is the span of a set of vectors. It's very quick if you can show that. If you're trying to show something is not a subspace, it's very hard to show it's not the span of a certain set of vectors. So that would be difficult. But usually it's pretty easy to show that one of the conditions of being a subspace fails, either A, B, or C. The quickest one is the zero vector. So that's the low-hanging fruit. If you want to show something's not a subspace, if you can show the zero vector's not in there, that's the quickest. Sometimes it will be in there and you'll have to move on and try and show you don't have closed under addition or you don't have closed under scalar multiplication. So I'll just do one more quick example with you. Let's look at the set of vectors. Let's let H equal the set of vectors in R2 of the form 1 A plus B such that A and B are real numbers. That's a silly example. No, I'll just go with it. Okay, this is not a subspace. This is not a subspace of R2. So I could use any one of the following methods to show it's not a subspace. First one, the low-hanging fruit. The zero vector is not in there. So 1, 0, 0 is not in H. Because 0 is not equal to 1. Vectors in H have to have first coordinate 1. So that would be the easiest. So, or you could say, or you could take two vectors in H. You could take 1, 3, that's in H. 3 is 1 plus 2, that's a real number. 1, 4 is in H. 4 is 2 plus 2, those are real numbers. Okay, so those are two vectors in H, but their sum, so let's call this U, and let's call this V. U plus V is 2, 7. That's not in H, because you got a 2 up there, not a 1. And you could also show scalar multiples are not in H. If you take 1, 3, that's in H, multiply by -1. Let C be a -1. You get a -1 at the top. So this one fails all three axioms. So that was a kind of bad example on my part. I meant to pick one that where only one of the axioms failed. You only need to have it fail one axiom. But that is an example. Okay, next time we're going to look at some very distinctive and famous examples of subspaces, column spaces and row spaces and null spaces.